Have you ever seen a headline that says, I don't know, coffee is amazing for you, and then a year later, another one says it's terrible? It feels like science just can't make up its mind, right? Well, what if I told you there's often a hidden culprit at work? Today, we're going to open up our detective kit and uncover the secret biases that can totally warp scientific results.
All right, let's just jump into a real case here. Back in 1981, a major study came out and bam, it linked coffee drinking to pancreatic cancer. I mean, people were freaking out. But then, later studies looked into it and they couldn't find that link at all. So what gives? Was that first study just completely wrong?
And that right there is the central mystery we're diving into. How can really smart, well-meaning scientists, using what look like totally valid methods, end up with completely opposite conclusions? The answer isn't that science is broken. It's that science is a human process. And because of that, it can have some hidden flaws. And the prime suspect in our investigation is a little thing called bias. Honestly, this is one of the most important concepts to get your head around if you want to understand research. It's the skeleton key to figuring out why two studies on the exact same topic can tell you two totally different stories. So what even is bias? Put simply, it's a systematic error. Think of it like a flaw that's baked right into the recipe of the study. It's not a random one-off mistake. It's more like a thumb on the scale, constantly pushing the results in one direction away from the real truth. Now, it is absolutely crucial to understand that bias is not the same thing as random error or, just bad luck. Random errors can pop up in any study, especially small ones, and they can make the results jump around a bit. But bias is different. It's a predictable glitch in the system itself. This analogy just nails it. Look at the left. Random error is like taking a bunch of shots at a bullseye. They're kind of scattered all over the place, but on average, they center on the target. Now look at the right. That is systematic error, or bias. It's like the scope on your rifle is misaligned. Every single shot is off, and it's off in the exact same direction. The error isn't random. It's built in. That is the difference. So in our detective story, bias rarely works alone. It's got two main accomplices that cause most of the chaos. And we're going to investigate each of them. First, selection bias, and then information bias. Let's meet our first accomplice, selection bias. The easiest way to think about this is like you're creating an unfair guest list for a party. Imagine you want to find out your town's favorite food, but you only survey people coming out of a pizza place. Your results are going to be just a little bit skewed, right? It's all about who gets invited to the party. So here's the bottom line. Selection bias happens when the way you pick participants is flawed. For some reason, certain people have a better or worse chance of getting into your study. And that means the group you're studying doesn't actually look like the bigger population you're trying to understand. The guest list was basically rigged from the get-go. And this is exactly how that unfair list gets made. You start with this big, diverse population you want to know about. But when you go to draw your sample, when you send out the invitations, something goes wrong. One specific group gets overrepresented, and boom, your final sample doesn't mirror the real world anymore, and any conclusion you draw from it is going to be distorted. I love this analogy. Think about a police lineup. Selection bias is like rigging it so the person the detective already suspects is, the only one wearing a red shirt or is way taller than everyone else. The process isn't fair anymore, and you're way more likely to get the result you are already leading towards, whether it's actually true or not. Okay, on to our second accomplice. This one is super sneaky. It's not about who you ask, it's about the answers they give you. We're calling this one the faulty testimony, or more formally, information bias. So, information bias happens when the data you collect is just wrong. It's inaccurate. People end up getting put into the wrong boxes. For instance, someone who was exposed to a chemical gets listed as unexposed, or the other way around. There's a technical term for it. Misclassification, and it just messes everything up from the inside. One of the most common and frankly most relatable forms of this is something called recall bias. I mean, we all know our memory isn't a perfect recording, and in a scientific study, that little imperfection can cause a massive problem. Let me show you how this plays out. Imagine a study asking people about what they ate 10 years ago. Now, a person who was just diagnosed with a disease, they might be searching their memory thinking, what on earth could have caused this? They'll remember every single burger they ate. A healthy person in the study, they might just give a casual best guess answer. Their memories are literally behaving differently, and that systematically skews the results. So what does this actually do to the numbers? This right here is the aha moment.
This term odds ratio is just a fancy way of measuring how strong a link is. So let's say the true odds ratio is 4.0, which means there's a pretty strong link. But because of recall bias, your study spits out a 6.0. You still found a link, sure, but you've exaggerated how strong it is by 50%. The bias didn't just tweak your result, it fundamentally warped your conclusion.
Okay, so now that we've identified our main suspects, it's time to give you your very own bias detection kit. We're going to turn you into a science detective, totally ready to give the side eye to the next study that pops up in your newsfeed.
And you know what the best part is? You don't need a PhD for this. Seriously, the goal isn't to go around debunking every single study, it's just to be a smart, informed reader. All it really takes is a little bit of curiosity and knowing the right questions to ask.
So here they are, the key questions in your detective kit. First up, always investigate the guest list. Who was actually in this study, and maybe even more important, who got left out? Second, you got to scrutinize the testimony. How did they get this information? Was it based on someone's fuzzy memory from 10 years ago, or was it an objective measurement, like a blood test? And finally, look for other clues. Could one group just be getting more checkups, which would make them more likely to be diagnosed with something? These are the questions that help you spot the bias.
You know, it can sound really complicated, but it all boils down to these two ideas. Just two main culprits to keep an eye out for. Every time you see a new study, just ask yourself, was the guest list fair? And was the testimony reliable? If you can just remember those two things, you've basically unlocked the secret to being a much smarter reader of science.
So, we'll leave you with this. Armed with your new detective kit, the next time one of those surprising health headlines pops up on your screen, what's the very first question that's going to come to your mind?